Thanks for that introduction. My name is Barry Becker. I'm a software developer at ESI working on a mindset product. I'm going to describe the way that we visualize our implementation of the Spark naive Bayes classifier. In this talk, I'm going to explain what a naive Bayes classifier is, how you can visualize it, and why you would want to. I'm going to describe some of the limitations of the naive Bayes classifier that comes out of the box of Spark and how to get around those limitations. And I'll attempt to give a demo and along the way provide some motivational use cases. So what is a naive Bayes classifier? It's a form of supervised machine learning. More specifically, it's a probabilistic model based on Bayes' rule that allows you to predict some small set of categorical labels or categorical values. And this small set of values comprise the target. That means the column that you're interested in. So the way that it works is described by this diagram, and I'll explain it by using an example such as credit card fraud. So the way it works is you start with some training data that consists of perhaps historical credit card transactions where you know whether it was fraud or not. You feed it into an inducer, which in our case will be a Spark pipeline, and that will create the classifier model, which could be evaluated using test data that's held out from the training data, or perhaps using cross-validation. But more importantly, it can be used to classify new transactions that are coming in that you don't know are fraud or not, but you want to find out. So they come into the classifier, and it will add a new column, which is whether it was fraud or not, or the probability of it being fraud. So there's some nice advantages to this form of classifier. It's very fast and easy to parallelize, and fast to compute and easy to parallelize, and it has a very simple structure, which makes it easy to understand and lends itself to a nice visualization. Its disadvantage is that it has this attribute independence assumption. And although this seems like a very severe restriction, even when this assumption is not met, the model performs quite well in most cases. It's very robust. The times where you'll really notice the problem, or when the main drawback, is when you have attributes that have a lot of interaction between them. Like, for example, longitude and latitude clearly have a lot of interactions. The model isn't going to be able to learn anything about those interactions. So you might have to create a new feature that combines them somehow. So I'm going to explain some more about how this classifier works using this mushroom dataset from the UCI machine learning repository as a simple example. So this dataset consists of thousands of different mushrooms that have been an expert has painstakingly gone through and classified as either poisonous or edible, and they've taken measurements about many other attributes of the mushroom, like its odor, its cap shape, veil color, and all of these things. At the bottom, this distribution we'll call the prior probability distribution, and that is the distribution of edible and poisonous mushrooms in this training data. So what we want to try to do is, when we get a new mushroom that we just picked, find out if it's edible or not based on all these other attributes. And how do we do that? We can use Bayes' rule. So this expression represents application of Bayes' rule for this mushroom case. So we want to find out what's the probability that it's edible given some set of factors. And in this case, the set of factors is going to be that it has no odor, spore print color is chocolate, and its ring type is evanescent. Now, this expression on the right is only going to work perfectly well if these three things are completely independent from each other, which may or may not be true. But even if they're not, it still gives a very good approximation to what we're trying to find out. And this expression on the right is read, the probability of these three things being true, given that the mushroom's edible, times the prior probability that it's edible, which we saw in the last slide is about 50%, divided by the probability of these things happening together. And it turns out that these three terms on the right are very easy to compute given the record weights that are accumulated in the classifier model. So this is very difficult and tedious to compute by hand. So what we've done is we have created a visualization that will allow us to interactively apply this Bayes rule and apply data to the model. So what we're looking at right now is our visualization of the structure of the naive Bayes classifier model that was produced for this mushroom data set. And what you're seeing at the top is that prior probability distribution of the training data that shows you the proportion of edible and poisonous mushrooms. And beneath it are all the other attributes ordered by their importance or their value for predicting the target, which in this case is that edibility. So it turns out that odor is the most important feature. If the mushroom smells bad, like fishy, foul, or musty, it's poisonous. If it smells like almond or anise, then it's edible. But if it has no odor, then it's got a mixture of both. So for each attribute, and there's lots of other attributes that aren't listed. I can't scroll down, it's just an image. But for each of these attributes, you're seeing a histogram, which gives you an idea of how the data is distributed. And for each bar in the histogram, the height corresponds to record count, and you can see by the color the distribution of edible and poisonous mushrooms in it. Now, what we want to do is we have our new mushroom. We want to try to figure out if it's edible, so we can select the values that correspond to what we saw as X, such as the ring type being evanescent, spore print colored chocolate, and there's no odor. And it will multiply together these three bar charts. So there's a conditional probability distribution represented by each of these bars. The model multiplies them together and then normalizes it in order to come up with the posterior probability distribution, which is what you see at the top here. And you can compare it to what you had originally with the prior probability. And that allows you to do this interactive classification. Now, this is one way to look at the model data, but there's another way which has a different use, and this is called the spinogram chart. So here was a histogram where the height of the bars correspond to record weights, and the width is constant. But in the spinogram approach, the height is constant, and the width corresponds to the record weights. And this is more useful because it allows you to compare how the distribution changes from one value to the next. So now I'm going to get into some of the limitations of the version of naive Bayes that's provided with Spark. Probably the biggest one is that the one in Spark really only works for document classification type problems. And we wanted to have a version that would work for any sort of data. So I had to rewrite it in certain ways, and I have a new version that exists in our fork of Spark on our public GitHub repository. And I'll explain the differences between the two, and there's also a lot of similarity. On the left is the version of Spark where every feature represents a word in a document. So the prototypical case is you're trying to classify spam, for example, from emails, whether emails are spam or not. So you might have a bunch of terms. I have 3 terms here listed just as an example, but there may be many others in your model. And for each term, you're going to come up with a relative frequency distribution. So for example, for all the emails in your training data that contain the word loan, slightly more are not spam than spam. But for emails that contain the word Viagra, almost all of them are spam. And for emails with the word zebra, almost none are spam. And so if I have a new email and it contains the word loan and zebra, and maybe other words, but we're not going to consider them for simplicity, what I do is we'll multiply together the 2 pie charts for loan and Viagra, which have those relative probability frequency distributions, normalize it to come up with the third posterior probability distribution, which gives us our prediction because the largest slice is orange, so that means not spam. Now, how did the email contain Viagra in it? That would skew the result much more toward it being spam. On the right is our more general approach. And now every feature is a column, not just a single word. And for every column, you have many different values. And if the column is continuous, we need to discretize it so it has different values. And for each of those values, we're going to have a distribution with respect to the target. So the way that we apply this model is kind of similar. We're going to have more of these pie charts in the case on the right, but it's similar the way that it works. So for this mushroom case, we know that there's a certain distribution for all the mushrooms that have the evanescent ring type, and so we're going to multiply that times the distribution for when there's no odor times the spore print color chocolate to come up with the final probability distribution, which tells us that it most likely is poisonous and you should not eat it. So these two core algorithms have a very strong restriction in that all the data that you give to them has to be non-null, non-negative integers, and that's typically not the way your data is. But it's this way because it allows these core algorithms to be very simple and performant. I mean, there's no complexity. All that complexity is going to be outside the core algorithm. And so how do we handle the data when it has nulls in it? And Spark, in some cases, doesn't really like to handle nulls very well, so we have to address that. What about string-valued columns? What about continuous columns, which are either floating point or date-valued? I'm going to call date values continuous because you can represent them as seconds from the epoch. And what if the target is continuous rather than discrete? So talk about each of these things. If you have string columns in your data, the first thing we'll do is we'll replace all the null values with some distinct, some special null value that's distinct from all the other ones. And we can use string indexers to map those string values into integers. And then lastly, after the prediction's done, we can use a string index to string transformer to get back to the original string value. Now, continuous columns present a special problem. There's different ways to address it. The approach we're taking is we're going to discretize them, but we don't want to just discretize them in any normal way, like using a uniform binning or maybe equal weight binning. Instead, from the literature, we know that entropy-based binning approach will give us the most predictive value from the column. And the flavor of entropy-based binning that we selected was called the minimum description length principle. It was invented by Fayed and Irani in the 90s. And we selected it mainly because there exists a very nice open source project written in Spark that will do this for us. So we're using this library. And what it does is it tries to find cut points. When it does the binning, it tries to find these cut points such that the differences between adjacent bins, the differences in the distribution with respect to the target between adjacent bins is as maximum as possible. Furthermore, we're also going to replace nulls with NaN so that they'll be captured in a separate bin, and we won't lose whatever predictive value there is from them. So let's look at an example where we have a data set with some continuous variables. This is a job application data set where we're trying to understand how the job being applied for relates to all the other fields that are in the job application. And this first most important attribute, the total estimated fee, turns out to be one of the best predictors of what the job type is. And so this entropy-based binning approach is nice because it will pick out regions like this red bar where it isolates regions that are very pure with respect to the target. So if you know that you're within this very narrow range, you're almost certain to be this DM job type. Similarly, if you're below this threshold of $128, well, then you're almost certainly either the blue or the purple job type. And similarly with initial cost, there's an important threshold around 1 that's picked out by the binning algorithm. And if you're lower than that, then you're green or purple. So let's look a little closer at that total estimated cost or total estimated fee column to see to try to get some intuitive understanding as to why this entropy-based binning gives us more predictive value. So on the bottom is just a simple uniform binning where I divided it into 30 uniform bins. Actually, there's a bin at the end which captures a whole lot because this actually is a very long tail as far as the values. But as you can see, most of the data is skewed to the left. And there's a lot of information there that's being lost in that 30 uniform bin approach. But with the entropy-based binning at the top, you can see here's that red bin where it's isolating that. And it's breaking the part that's on the left up into a lot of very fine-grained bins because it's seeing a lot of value there where it can make some bins that are very pure with respect to the target. And then on the right, there's almost nothing happening, and so there's very few bins there. I'm going to show this exact same thing now using the spinogram view. So there's no difference in the data that's being shown, but now there's a one-to-one correspondence between the values on the x-axis, and those two vertical blue lines are parallel because of that. And again, you can see this bin in the middle where in the uniform binning, there's a lot of red lumped into this very wide bin, but the entropy-based binning is going to isolate it. So the basic principle behind what this binning approach is trying to do, it's trying to maximize the amount of information gain with each split that's added while minimizing entropy and the amount of disorder. The algorithm recursively subdivides the bins until it basically gets diminishing returns. So the stopping criteria has two components. If the information gain that you get is too small, by adding another further cut point, it won't do it. Or if the bins themselves are getting too small, it's not going to continue to subdivide because it'll lead to overfitting, which you don't want. And at the bottom, there's a link to the open source project that does this MDLP binning. It was created by Sergio Ramirez. And it's very nice because it will work on lots and lots of columns all at the same time, unlike the bucketizers in Spark, which really only can be applied to one column at a time. So another thing that can happen is sometimes a user wants to predict a continuous target. And normally, you wouldn't use a classifier for this. You would use a regression type model. But we want to get the value from the visualization. So what we can do is we can uniformly bin the target column. We can't use the entropy-based binning because we're actually binning the target. And we don't want to use uniform binning because the data may be very skewed and we might end up with empty bins. So we use the quantile discretizer or quantile bucketizer within Spark to come up with these 3 equal weight bins. And in this example, we're trying to predict income based on these other attributes. And so you can see how different demographic properties of people like occupation and hours per week worked and so on can relate to their income. OK, so now I'm going to attempt to give a demo of Mindset, which is the product that we're working on. Let me close this part. OK, so what we're looking at here is some felony incidents from New York City crime data, and we're trying to predict what kinds of offenses might occur given other factors. And it turns out a precinct is one of the best predictors of what kind of offenses occurred. This first attribute, precinct, is a nominal attribute, means it's orderable. And by default, it will order the values by whatever the majority class is. The majority class is grand larceny because that's what happens most in the training data. And so all the precincts with the most grand larceny appear at the left, and the least are on the right. And then there's a little value here, NA, that has hardly any data in it. And as we scroll down, we can look at the other attributes. And well, you come to a point where you can see that Staten Island has far fewer crimes happening than or reported than Manhattan, but you can't tell the difference in the distribution. So what we're going to do is we're going to switch to the spinogram mode, which will allow us to compare the distributions between these values more easily. And now we can see that Manhattan has far fewer motor vehicle thefts than the other boroughs. For some reason, maybe that's because fewer people own cars in Manhattan, I'm not sure. Let's see what else we have. OK, so one thing, though, that you might notice is there's certain classes, like murder and rape, that don't happen very often, but maybe you're interested in understanding where and when they happen. And it's difficult to see that in these charts at the bottom because they happen so infrequently. So for that, we can switch to an evidence mode. And what that's going to do is it's going to divide by the prior probability distribution at the top in order to normalize all the colors in each of these bar charts at the bottom. So if you have a bar that has all equal color in it, that just means that the distribution is basically the same as your prior probability distribution. And there's not too much interesting happening there. But we can see things now. We can see the differences in distributions or differences in evidence for different crimes among the different boroughs. You can look at the occurrence hour of the day and see how, like for the early morning hours between midnight and 5 a.m., there's more murder and rape happening than there is during the mid-morning hours between like 8 and 12. And you can also do these what-if scenarios. So for example, suppose you know that you're in the Bronx and it's Sunday and it's, say, 4 a.m. in the morning. Oh, I didn't mean to do that. Let me go Bronx. And it's Sunday. So now at the top, you can see this posterior probability changing as I select things. And it's showing me what my expected probability distribution would be. And you can see that suddenly felony assaults is much more likely and murder is more likely. So even though murder happens very infrequently at 1.5%, it's still 3 or 4 times more than the baseline rate. So it's telling us that there's like a boost in evidence for that particular offense, given those factors. There was one other interesting thing that kind of shows up in this mode is that the murder cases all have very low or very high object ID. You can see that by this purple slice. And sometimes you were interested in just a specific class, like murder, say, and you can click on that class, and now all the nominal attributes are going to be sorted by most evidence to least evidence for predicting murder. You can see those low and high object IDs suddenly became huge. In fact, maybe it might be more useful to look at this in the histogram mode, so you can see those huge amount of evidence for low and high object IDs predicting murder. But you could also look at, say, hour of the day, and you can see very clearly how there's more evidence for murder in the early morning hours than in the mid-morning hours. And evidence is it's a negative log of 1 minus the conditional probability, but the reason it's computed that way is so that you can add evidences. So you can take this evidence value from different attributes and add them together. So for the things that you know, you add together those evidences, and it tells you the total amount of evidence for that thing. Another thing that's kind of interesting is this in the precinct, that NA value shows up really strongly here. And that's because even though there's very few cases that are in the precinct NA, not applicable, almost all of them are murder cases. OK, now to switch back. So throughout this presentation, I've been showing a lot of little bar charts. And sometimes some of the slices within that bar chart can get really small and get lost if you're not careful. So we actually invented a new way of rendering these bar charts so that won't happen. So the traditional way of rendering bar charts is to use anti-aliased rendering. And in the case that's highlighted here, these very small segments can easily get lost when you're using this approach. And the reason for this is the height of the rectangle that represents that small slice doesn't align with pixel boundaries. And in the case of this orange slice, it's even much less than 1 pixel, so you don't see it at all, and it ends up blurring, and the colors mix, and it can kind of be very misleading. So what we've done is we use this pixel perfect rendering technique at the top, where the number of pixels that we use to represent that small slice exactly corresponds to the proportional amount of area based on record counts. And so unless your data is, or your number of records is much less than the amount for 1 pixel, you're guaranteed to still see that slice. So you can see these little tiny orange bits in there, I hope. Whereas in the bottom case, you would totally miss them. So in conclusion, The Spark knife-based classifier can be applied to any sort of data as long as you make some modifications. The minimum description length principle is very useful for bidding continuous attributes so that you can get the maximum amount of predictive power from them. And visualization of the classifier model not only provides you some really great insight into your data, but it gives you some level of trust that your classifier is working as it should be, and it helps to explain why predictions are being made, so you can really get in there and kind of understand why a certain prediction is made. And it gives you this interactive ability to run what-if scenarios and ask questions about any sort of set of attributes. For things that you know are the case, you can find out what the prediction would be. So thanks for your attention. This is a link to the product and my contact information. So if you have any questions, I think we have a few minutes.
So for questions, there is a mic in the middle. And
hi, how do you treat null values? Do they have a correlation or no correlation? And
How do you treat what?
for null missing values, do you treat them as having a correlation or not having a correlation?
We do account for the null values. We treat them as a separate value. So they're pretty much treated just like any other value.
Okay, and do you support features where you can have multiple values, like things that I like, where you not have only one, but multiple?
I'm not sure I understood the question completely, but one thing I should mention is that there's sometimes you have features with many, many values, and we would just, if there are more than 100 values, we throw them out, and perhaps we shouldn't. One of the things we might consider doing is like trying to group them. We haven't done that. Sure. So that was for the open source project that we used. And I don't have the GitHub link for our own fork, but if you search for ESI mindset, you can find it.
okay, let's give Barry one more round of applause.
Thank you.